of E2 reactions. That's elimination reactions. And we're going to talk about regio selectivity, stereo selectivity, and stereo specificity. This, I will tell you at the outset, I don't think there's any way at all to do this without practicing a good deal. I'm not sure that the homework practice that I give you is going to be enough for you to be comfortable with this on a test. You need to be making up your own reactions. I will demonstrate this in class, but I encourage you, strongly encourage you, to practice this until you like it. All right? So here it goes. It's common for a substrate to have more than one beta carbon, right? That can be deprotonated by a strong base. So for example here, let me come here. Here I've got a beta hydrogen here. A beta hydrogen here. I've got 3 here, right? 3 here because that's a methyl group. But I also have 2 here, right? So the question is, which one is going to be deprotonated? This base is going to come here or here, right? And deprotonate that. If it comes here, this is going to go here, and the leaving group's going to go. There's my E2 mechanism. You need to, hopefully you've practiced that already, but you need to practice it. So my E2 mechanism is either going to be that way, 1, 1, and 1, or 2, right? 2, 2, right? Can you see that? And the leaving group will be leaving also. That's part of 2. So this is going to get very busy, and you need to practice this, all right? So if we go pathway 1, then this is going to be the product. Can you see that? You're going to have the double bond over on that side. All right? So that's going to be the product of pathway 1. If you go pathway 2, this is the product, right? Can you see that? You should practice this. If you don't like that, you need to stop the video now. And if you don't, folks, I'm telling you, this is going to be a difficult path if you don't practice. I know. I keep saying the same thing. All right. So when ethoxide is used as the strong base, 2-methyl, I just said that. All right, so we get the Zaitsev product or the Hofmann product, depending on which way we go. Now, if we use ethoxide, that's what this is. If we use ethoxide, then we're mostly going to get the Zaitsev product. Okay, why? Well, the reason why you could prove this to yourself by using the Hammond postulate, drawing the intermediate, or not the intermediate, the transition state. Draw the transition state of both of those. And there's lots of lines and dots in it, right? So, but if you do it, you'll be more inclined to appreciate why that is the case. So, first thing you need to memorize that it's the double bond is going to go to the more substituted double bond if the base is small, right? This is a relatively small base. If the base is bigger, watch. If the base is bigger, like terbutoxide, right? I don't even know the name of this, but this is huge, right? That's a really big base. And in that case, we can drive it toward the Hofmann product. All right? So Zaitsev product for a small base, Hofmann product for a bigger, bulkier base. And you'll have to recognize these on an exam, right? So if I were writing this on an exam, I wouldn't probably write it out like that. I probably would say CH3CH2. Watch this. 3O with sodium or potassium as the counterion, right? So these two are the same thing. And I've been encouraging all along to appreciate what structures are. Why did I put the sodium here? Why did I put the sodium here and not here, right? I've answered that a couple times. And so you've got to be ready for that. So a couple more strong bases, which are big, sterically hindered, which will give the Hofmann product, are terbutoxide we saw in a previous slide, terbutoxide, diisopropylamine, right, and triethylamine. So these are all real big and bulky, and they're going to be more likely to give you the Hofmann product. That is the less substituted double bond. All right, so I now want to talk about stereo selectivity, okay? So, and if you have, suppose that you've got some what is this? This is a symmetric alkyl halide, right? And you've got a good, relatively small, strong base. this is going to come in, so it doesn't matter which side it comes from, right? This is going to come in and take that hydrogen. These electrons are going to go to that, into a pi, and the leaving group's going to go, I'm just practicing my E2, right? You see that? Well, that's all well and good, but the question is it going to give you E, or, well, that's E, or trans, right? Or is it going to give you Z, or cis? Which is it going to give you? Well, you see here, in this case, it's going to give you, the major product is going to be the trans. Why is that? Now, I'm not going to tell you. If you want me to tell you, then you need to come and ask me, and I'm going to ask for the energy diagram. I know in a way I'm sort of, that's a barrier for you to come and ask me, but you ought to, right? You ought to draw the energy diagram, use the Hammond postulate to draw the transition state, and that will help you answer it. If you can't do it, come to me, but I'm going to require that you try. All right. So we're generally going to get the trans, and it's frankly it's easy enough to memorize because these guys are big and bulky, right? And they want to get away from each other. So this is going to be more stable. But again, I strongly encourage you to draw out the transition state and of this. It'd be a great test question. I probably should do that on a test, shouldn't I? All right, now consider the dehydrogenation via the E2 mechanism of this alkyl halide, right? So we've got this big, ugly alkyl halide phenyl group. pH really just mean this is just the same as having a big benzene ring, right? So this right here is just a big benzene ring. We like to save time in economy. There's a methyl group, right? That's a CH3. So this is complicated to draw. So we draw pH, but you can't forget when you see that pH, you know you're dealing with a really big system, right? So you got a phenyl group right here, a methyl group, a bromine, and a hydrogen. Well, look here. This is a CH3. You can see that. Here's a CH3, okay? So there are no beta hydrogens on this side, none. There are no beta hydrogens on this side. So you know that the base is going to take that hydrogen right there. You know that. You also know that these electrons then are going to go to make a pi bond, and the leaving group is going to leave, right? I'm practicing the E2 mechanism when I do that. It looks like my sister wants to talk. I'll have to get back with her in a couple minutes. Yes, I can talk. I'd love to talk to you. So here's my base coming in, hydrogen, boom, 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 okay? Now, having said that, the question is going to be, are you going to get the cis or the trans product, right? So it looks like here you would expect, this is not cis or trans, this is going to be E or Z, right? That's going to be E, because I look down that double bond, here's the bigger one on this side. I looked on the other side of the double bond, here's the bigger one on this side. They're on opposite sides, and so that's going to be E, right? That's going to be the E isomer. Now, the Z is not formed at all. So again, you can sort of appreciate why it's not formed, because they're big and bulky, and you go, yeah, they're big and bulky, but there's a better explanation which you may be called upon to appreciate at some point, or to demonstrate understanding of. It turns out that the transition state needs to be in the lowest energy conformation, and it needs to be what we call I'm going to call it anti-coplanar now, but pretty soon we're going to go to anti-periplanar. So watch this. When you draw these mechanisms, you need to draw the hydrogen and the bromine opposite each other. And I'll show you why in just a second. But I've got my base. Still just practicing the same thing, right? Comes and takes that hydrogen. These electrons go to a pi bond, and the leaving group leaves, right? Again, just practicing the E2 mechanism. Now, why does it have to be coplanar? Why do these all have to be in a plane? Can you see that all four of these atoms are in one plane as I've drawn it, right? Because they're all in the plane of the screen of your computer. Okay, why? Well, here's the reason why. If you consider the Newman projection of this, right? If they have to be in the same plane in order for these electrons, these are also in the same plane. Those four atoms are also in the same plane, but watch. In this case, we have, these guys are all staggered. You see this phenyl group? It's staggered with that tert butyl group. But if you pull this around and put these in the same plane, but now they're eclipsed, then that tert-butyl group and that phenyl group are also eclipsed. And this is a nightmare. I mean, those guys are huge, right? So they're not going to be eclipsed. Let me go back a slide. I'm going to go back a slide. Actually, I'm going to go back 2 slides for a second and say that this isomer is simply not formed. It is not. It doesn't happen, right? Why? I'm going back forward 2 slides now. This is the reason why. That if you look at this down the Newman projection, you can see that these 2 beasts right here do not want to be eclipsed. All right? When we draw those with letters and lines and such, we can maybe make it look like they're a long ways away, but they're not far enough away, nearly far enough away for that to not be an issue. Okay? So let's go to appreciate this with a few more details. It turns out that it doesn't have to be exactly 180 degrees across from each other. Let me go back. You know what I mean by 180 degrees? This is 180 degrees, right? Right? Where, can you see, we're looking down that bond right there. So this bromine and this hydrogen are 180 degrees away from each other. Here they're 0 degrees away from each other, or, you know, because we offset them so we can see them. But by that structure, we mean that they're eclipsed. So we're going to I skipped a slide, didn't I? Let me go back here. And let me just remind you, I just said this a second ago. This is the low energy one. It's staggered. And this is high energy because it's eclipsed, but this is the really nasty eclipse right here. Okay? And so if you do that, if you take off that hydrogen, your base comes off, takes off that hydrogen. These go into that bond, which is we're looking down the axis of as a pi bond, and this leaving group leaves. I know, just practicing the E2 mechanism, right? Keep practicing. Follow my example. Just keep practicing. Can you see if that hydrogen leaves and that bromine leaves? These 2, this methyl group and this phenyl group, are going to come down, right? And this tert-butyl group and that hydrogen are going to go up, and it's going to give this, right? Just exactly what you would imagine. If this is not obvious to you, I strongly encourage you. No, I will compel you. I will tell you. If this does not make sense, stop the video. Build this structure. Build it with your model set, and then take off the bromine and the hydrogen and see what you have at that point. This will make a lot more sense, right? That's your marching orders to do that if this is not already obvious. Okay, more details now. Evidence suggests that the strict 180 degree angles is not required. And so it turns out, if we've got, as long as we've got something close to 180, that's fine. And it turns out then that we don't use the term anti-coplanar, we use the term anti-periplanar for that reason. All right, and let me go back to something else. We learned in previous conversations that the E isomer is more, the E isomer is usually more stable. But because of considerations like this, sometimes we can force the less stable Z isomer if we consider the anti-periplanar requirement. Right? It would be a good question, a good test question. You should make one up. You should make one up to force the stable Z isomer. Okay, so now for the following substrate, the beta carbon has 2 hydrogens, right? Look here. Here's the leaving group, alpha, beta. So there's a hydrogen and there's a hydrogen. In that case, the hydrogen that's going to leave is the one that they can both get anti-periplanar, right? But the hydrogen that's going to leave is going to be the one that gives you the least stable, the most stable double bond. So if these are all the same size, if R1, R2, and R3 are all the same size, then these are identical. But if R2 is the biggest, let me do that right there. If R2 is the biggest, right, and I said R2 was the biggest, right, then you could see that R1 would want to go on the other side, right? So this is stereoselective, but not stereospecific. It doesn't require that. You'll get a major and a minor product here. So just to review the terms stereoselective and stereospecific, this is a stereoselective means that you can get a major and a minor product from some reaction. Stereospecific means that if you have, green, you're only going to get green, or if you've got this other thing, you're only going to get something else, right? Stereospecific means one configuration will give you one product and the other configuration will give you another product, and stereoselective means you're going to get two different, they're going to be competing. All right, I think I'm almost done here, but let me go there, and then here's my last slide here's my last slide for this conversation. Consider the dehydrogenation of a cyclohexane derivative. Now recall that if you have these in antiperiplanar, you can get good E2. But if you don't, and there's no hydrogen that's antiperiplanar to that, this is not going to happen. So in order for this to eliminate, the chlorine, though it is the higher energy conformation for it to be in the axial, right? Here it's an equatorial, but there is no hydrogen that this can eliminate with. So elimination is not going to happen with the chlorine in the equatorial position. Only going to happen with the chlorine in the axial position. And that's all I want to say about this. This is going to require a lot of practice. I encourage you to maybe watch this video again and follow with me. Go through and do the mechanisms with me as you go. If you're passive about this, I would say to a high degree of certainty you're simply not going to get it. You have to pull your pencil out and draw these mechanisms out. Of course, the homework is going to require you to do that, but how thoroughly you engage the homework is up to you. And so I wish you the best. Don't shy away from what is likely to be a very uncomfortable, at least in the beginning. Good luck.